Good morning, everyone. And, this is my name, Xinji Chen from the CAC2, and I'm in charge of the CAC2 surface analysis facility. And today's topic, I talk about the principles and practical technique of XPS. XPS is quite a popular and very useful technique and in our center. And I think maybe now still more and more users and trying to learn this. And basically, I want to give the basic and also the technique what is this, and help you understand. So what is XPS can do, cannot do. Okay, so basically this is like this X-ray generated photoelectron analysis spectrum. On the picture, you can see this. We have two like this. Left one is SKLab. That is what we have, and that is quite a popular instrument, and there is a lot, the advanced function of have this. On the right one is like a simple version, like K alpha. That is, we hope, and we can get another one, because this XPS, if you look at the resolution, the book that is quite busy every day, and from the early morning till night is booked. And we hope, and by the end of this year, we can get another XPS. For the regular routines XPS analysis, we go to this instrument. For advanced XPS analysis, you can use this. That is, we hope we can get something new. Okay, so in this talk, and first I will just a brief introduction about the CAC2, what instrument we have, what capability we have. And the next is XPS basic principle and instrumentation, introduce this, and the various characteristic technique with XPS. So any question, and you can type in the chat zone, and after the talk, I will answer and follow the order. Okay, so for CAC2, and besides, and we talk about XPS, and we also have other instrument like FTIR. This is quite useful and more popular. Special left one, this is micro FTIR, and the right one is regular like FTIR and soma FTIR. So this one we can run like a box sample, like powder, film, liquid, and this. If you have some small samples, very thin film or small spot, you want to use a microscope, use this one. You can take an image, and then you can locate it in a different area, take all FTIR from a specific spot and get this. This is quite very easy to use and very useful. We have ATR, that is almost no sample preparation, very easy to use. So this surface profiler, or in our side we call the stylus profilometer. So this one we use stylus like tip to contact the surface, get the profile. The left one is optical profilometer. Also we call the 3D optical microscope. We can easily get this 3D image and very quickly and easily get this. So this is a ellipsometer. So this is a technique to use the light and get through all the film from interface. For example, you have some film. We know a lot of people measure the thickness use a profilometer, but you have to make a step like a scratch as a surface and partially remove. But for some film like a silicon oxide, silicon nitride, or ALD, you made film, it's hard to remove. It's very stiff that is bounded to the substrate. So you use this method, you can use the light, get through this top film and reflect from the interface. And then we analyze this analysis spectra, and then we can get the thickness. Even we use a motorized stage, we can get the map, the map of the thickness. And also we can get an optical constant of this. Okay, someone maybe need to mute. Okay, so besides that instrument also, we will have, see this is very fancy, the instrument, and we don't have yet, but now in our lab, we have our top themes. That is from 5-3, that is 20 years used. Still functional, we can get nice spectra, but that top seems special the optical microscope. That is optical camera is not good, so it's very hard to see your sample. Use that setup, and also that stage doesn't have Z motion. Sometimes where focus the sample is difficult. And for depth profiling, even that have the gas gun, but each time you need to do do calibration for the spot. It's functional, but it's not very user friendly. But we will have this for sure, and by end of this year, this is like the latest version of the top SIMS. We call M6. For this SIMS, this is also for surface analysis. We can get a very nice, that is spectral, and for the mapping, we can get like a 50 nanometer letter resolution. We can have many the gas gun. This gas gun, just like XPS, what you use now, you just turn on, you don't need calibration, you can easily do the depth profile. And also for this one, we will have a FIB column. We can make a cross-section analysis. You just cut or part of your sample and tilt, and then you can do the mapping. He's very excited about this. We will get, end of this year. Okay, let's back to the XPS. And so we know the XPS use this light, get an electron. The original idea, actual discovery, is based on the Einstein discovery in the 1905. So they use the light source, and shine and bombard on the metal like a cathode. You can generate electron. You can get electricity here. You can get as a current. So this discovery, and Einstein get Nobel Prize by this discovery in 21. And this is just a basic idea discovery, but not practical for the analysis. But in the 1960, the Dr. Kai and Sagban in Sweden, they developed this XPS technique. Basically, you have to have a realistic electron analyzer. You have to analyze what energy they left for the electron, and then build the vacuum and also the actual source. And then so this Professor Segman and first developed this technique. And in Europe still, they called this ESCA. So that's why our instrument called ESCA Lab. So that is electron spectroscopy for chemical analysis. Yeah. So basically there's a different name, but I think now is more and more people called just XPS. That is, the name. Because this and the development and the Dr. Sagban awarded the Nobel Prize in Physics in '81. I just mentioned, this Dr. Sagban's father, and Sagban, was also awarded by the Nobel Prize in Physics in 19, because of the discovery and research in the X-ray spectroscopy in their family. Okay, too. Okay, just mention that. Okay, so this XPS, that is okay. So this X-ray you see here is, for example, silicon. This electron, there's a core electron or valence electron, and like this orbit this. So this core electron more stable energy, but this valence, okay, that can lose, can get more. So this X-ray basically can knock out this, can strike this here and knock out the electron. The electron come out, and then we analyze this energy. So this use the analyzer, we can measure this, get kinetic energy. So this is light, this X-ray energy, and already know. And for example, we use aluminum K alpha, the 1486, that already know. So this is a spectrometer work function, and we also know that. So based on this, we can get the binding energy. We can, from the binding energy peak, we can identify, okay, from which element. So that is, we get spectral binding energy basically is calculated. We directly measure this kinetic energy. So based on this spectrum, graph, I can show that. So yeah, this is another graph. Okay, this core electron, this valence electron. So use X-ray from core electron we get. This is called XPS. If you use a UV source, UV photon, the most get just the valence electron come out. And this we can get UPS. In our instrument, we also have a UV source, and so we can get a UPS. For XPS, you can get a core electron, these peaks. Based on the peaks, they identify element. But the valence band, this UPS, is mostly different element, different substance. Their UPS, they just a very small difference, like a homo position, a work function, just small. Based on that, you cannot identify element, but it still give you the information about this homo work function for this material. So UPS just gives this information. XPS, you can identify the substance. So these are basic components for XPS. XPS, first of all, this load assemble here, you have X-ray. So now most XPS use a monochromator. So this energy, this monochromated X-ray, that energy, the resolution much better than this. And then this is the analyzer of this detector. So here is the argon spot gun. Argon spot gun is basically you can etch the sample, you can do depth profile or surface cleaning. So we have now is mono and ion spot gun. In the future, I think about maybe end of this year, we try to get a cluster gun, argon cluster. Argon cluster is more gentle for the organic, and you can get better. You know, for this one, sometimes energy is strong, you can implant. So this, all the damage can be huge. So if we use a cluster gun, yeah, the damage on your sample will be less, and for depth profiling will be get better in the resolution. So this is a flood gun. In this instrument, we use the electron and argon ion combination to do the condensation for the insulating sample. Here's the camera. So this basically is the setup of the major component of the XPS instrument. So we talk about XPS is a surface analysis. So this is top layer, second layer. So X-ray get in, and from top layer, you see the electron just come out. Okay, this without collision, they just come out. For second layer, for deeper, when electron come out, they have to go through this, and there is more chance to make collision with other electron like this. If this collision is inelastic, if this collision is elastic, means doesn't lose energy. Okay, so this electron will contribute for the peak, for the band energy, for the peaks. If this many come out, the many collision, and there is an inelastic collision, that means they lost energy during this collision. So this electron cannot contribute on the peak because that is the energy already shift. Because that is when the measure use the analyzer, that is kinetic energy much less because here they lose energy. When they get loose, so that electron cannot contribute to the peak. They will be contribute to the noise like a background. So that's why on the spectrum you will see high binding energy side. That means high binding energy side. That means low kinetic energy side. That is a background get higher and higher. That because more and more electron. So that is head is the inelastic collision inside, and that contributes to the background. So because if it's deeper, because they lost, they cannot come out or cannot contribute for the peaks. So only the top or field layer can get information, yeah, for the spectrum. So this is another graph I get from Google. And so this XPS, this aluminum K alpha, this X-ray beam, and this analyzer, you see the electron, they come out. So this a layer, you see here, this layer with lambda, this lambda is electron mean free path. This mean free path depends on atomic number, depends on element. This is different. Generally, range is from 1 to 4 nanometer. This range. The heavy element you get a small, and the light element is big. So this, you see, based on this graph, this on first lambda, that means first like 3 nanometer, they get 60% information from the first lambda. The second lambda is 30%. On the third, this is only 8%. That means if each layer, this lambda, if there is a 3 nanometer, that means 9 nanometer. That is, you have 98% information come from this layer. So below, like below 10 nanometer, almost nothing. Electron cannot come out because all the bonds, they lost energy. So that is XPS, really, that is a top layer. If you have some like a coating or contamination, you just collect this contamination. You have to be remove this top layer, and because this only analysis top layer. And note that like you do the next video, I will show you EX. You know, you have to, for the incident sample, you have to do the coating. For this one, if you do the coating, you just analyze the coating and totally. So here shows this how much information from top second layer. Okay, so here's a comparison, and a lot of people know they have this EDX used. They use the EDX a lot, and EDX, I know EDX very good for especially mapping. You know, that is resolution very good. But XPS EDX different is EDX use electron, high energy electron, bomb the sample, and then they generate X-ray come out. Our XPS use X-ray, generate the electron come out. So that is inverse. So for the EDX, they get it, the X-ray is much deep. You see here, from here to here is around like a micron deep, even deep, depends on the element. See, this get information is from here, no top layer. So for XPS, we only collect here, this layer, only 1 to 12, okay, somewhere is 112 and 10 nanometer. So this information. So when you analysis the sample, select from EDX, from XPS, you have to be selected. You want to analysis the bulk material or just the top layer. So that is difference. Of course, there's other difference like quantification. Probably that is I think XPS is more accurate than EDX. Also for the element, like a light element, like boron, like lithium, maybe EDX is harder. But XPS, they can analyze all the elements except hydrogen and helium. So that's a comparison for these two techniques. And we mentioned about XPS is not just like can detect from the peaks and binary energy. These peaks, the core electron identified element. They also have the chemical information. Why they have chemical information? Because, for example, this is a core electron, this valence electron. When this, for example, you lose electron, this valence electron you lose, and then this core electron will be attracted by this nuclear with the force will be stronger. So binary energy will get higher. That means the binary energy will be increase. Here example, this is a silicon oxide on silicon. So this is a silicon peak. Don't look at this number. This number is the kinetic energy. We familiar about the binary energy. I put here 99. And for silicon, the binary energy is 99. And then if the lost electron, the silicon 1 plus, 2 plus, it get higher. We're also familiar about this SiO2, that is 4 plus. You see here is 103. 103. So for this silicon, if they lose the electron, get the positive, so this binary energy get higher. So that means this and orbit a little bit shift to inside, get stronger. this. So that is basically for the 2+, 3+ for this loose energy, the spectrum, you should expect this shift to higher. So for this, some like oxygen, chlorine like this, they gain the electron, they will shift to the right side. That means the binding energy go to lower of this. That is the difference. And you understand this, why they are this shape. Okay, so here is an example of the spectrum. Left is a surface scan. I always ask our user to get a surface scan. This gives you an idea on your surface. Sometimes you just focus on some element, but you have a surface scan, you have an idea what element on the surface. Based on this, you can get your survey ID, you can get this surface composition of this and get the quantification and identify the peaks. They not just here, this binding energy peak, also origin peak, they can show up this. But this just a very big step is course. We can identify peak, cannot tell you the chemical status, but you also need like a high resolution, like elemental scan. You see here, platinum. So here you can see this is platinum 3D, they have a split, that is what they have as for 3B. But here you can see a split, not split, here is a 2 peak. Why this happened? So these materials, the catalyst used in the oil industry, very common use. And our customer from BP, they commonly, they are routinely analysis this sample. So here you can see this shift. This, if we do the peak fitting, we can find, okay, here we can fit 3 peaks. Here, 1, that is metal. This one is 2+. Here is 4+ platinum. So this peak we can shift because this is a split. So each this status you need a pair. This pair, this pair, have a pair for this. And after this fitting, they give you the information. Okay, this the metal on 15%, the 2+ is 80%, the 4+ is 5%. So that is advantage of this XPS. They can tell you the chemical information. That is like it seems like EDX cannot tell you. So besides the surface analysis, we also can do, because that is only analysis 10 nanometer. Sometimes you said, I want to see deeper. And for example, 100 nanometer or even 200 nanometer, one deeper, want to see how the element change. You can use this argon spot gun. So we have an argon spot gun. This first you set up for depth profile. You set up the energy and the H time. You basically like this. First you analysis surface, and then you use argon H or layer. You can set up the time, how big, how long time, and then H layer. During the etching, the no analysis, and then you make new surface, and then you analysis this new surface, and then you etch again, your analysis again, like this. Okay, analysis, etching, every new surface etching, like alternate, so get many cycles, and then you can get all depth profile for this stuff, like this. So this is one example, and like the silver on the silicon surface. You see here is silver. So this energy, this is the time. So this spectra you see here on the top of field layer and of a field cycle, they have a silver, and then their silver is gone. And this on the top layer, because silver is covered, don't have the silicon. And then after this, so the silicon show up. So you use 3D and show this depth profile, spectra, how they change. This is very cool. Okay, besides depth profile, and this instrument, we also can tilt the sample. So here is a typical setup. The X-ray, 45 degree, here's a normal takeoff angle. And then you can get a 10 nanometer analysis. But if you tilt your sample like this, we tilt to like here we tilt like 80 degree, this angle only 10. And then we can analysis this one. This electron only come from here, from this layer. So if you calculate the sampling depth is 3 lambda sine theta like this, and this only 2-3 nanometer can get this. Okay, so this angle. So if you have a very thin layer, like a film, a monolayer, some of this, if you tilt, even the total count may be low, but the contribution from the top layer will be get higher structure. So here is the example. I use a native oxide layer on silicon. This native oxide layer only 2-3 nanometer. So if I take over angle is 90 degree, see this is SiO2. This is silicon. So for this layer, is contribution is less. If I tilt this 20 degree, here 20 degree, if I tilt this, and then I get this contribution from the native layer is much higher. So that I can enhance a signal. So based on this tilt. So this is just one angle tilt. Of course, this one we can set up, we can do the multiple this tilt and get angle result, this spectrum. So this shows you for the XPS and for the sample, you use the X-ray, the bottom of the surface, you get the electron come out. And basically here you have a hole. So you have this hole, and if your sample conductive, the free electron come here, compensate, you can continue to analysis. But your sample, if it's insulating, so this for the electron come out, here is a hole. This no free electron can move here because it cannot freely move. So this will build a charging. This build charging when the further electron come out. So this layer, they will be consumed, this energy, will lose energy. And then use the analyzer, they will analysis all this energy is less because they lose energy here. They make your spectral you shift because this spectral shift. This shift can be depends on how heavily insulating, can be a few EV, a few 10 EV, or a few 100 EV can be. If it's more than like a 10 or 20, you will get nothing in your spectrum. Basically, for the element, you just get a plus minus 10, like 20 EV. If you shift too much, you cannot get. So you have to turn on this charge compensation. So our charge compensation quite efficient, and you turn on. You basically for this instrument, you can analyze any solid sample, even glass. This PET, like this polymer, is no problem. This charge compensation is very useful. Okay, so last and I'll show you is we have also this heating and cooling stage, and this you can heat up to 300 C, and also you can use liquid nitrogen cool. You can cool minus 170 C for this. And you can do the heating cooling in analysis chamber. So you can do the in situ, this analysis. And in this talk, I didn't mention, and I just mentioned it, I didn't put that spectra. We also have a UV source. We also can do this UPS analysis. And others like ISS, like that is not often used. If somebody interested, we can talk and offline this. So basically for this technique, I have some summarized for this XPS, what they can do. Basically, they can provide the quantitative, this composition for this. And you have some material, you want to identify what it is, you can use this to analysis and get the quantification and composition. And then also tell you the chemical status of this information. And the detect is 0.05 to 0.1 to make this detect limit. This depends on the element. If heavy element get more sensitive, for light element, it may be just 0.1. So sampling depth is 10 nanometer, and it can be this can do point analysis line or map. You can do the mapping and do the area, do the mapping spectrum, and they can do the depth profile and the conductive insulating sample, all the works. And they can do any sample like a powder. You can do powder solid, but any sample, have to be, because all we talk about this analysis is in the ultra vacuum. The sample have to be compatible with ultra vacuum. Any like liquid, like this gel, like this sticky samples cannot, if they can destroy the vacuum, it cannot load. And also, if it have to be stable under the X-ray, if it's X-ray bombard, this something degrade, some change, and you cannot run that. Okay, here is a basic summarize like a prong run this XPS. They have this surface sensitive and all solid sample analysis fast and easy. We also have a nice software to analysis. So cone is letter resolution. You see, all I talk about, I didn't put the image. So that is the letter resolution not good because X-ray spot size, we can, that is a range from 200 nanometer, 200 micron till 900 micron. We can put the aperture to 20 micron, but we cannot get less. So the letter resolution is not that good. Also, you have to be UHV compatible. So this I just mentioned that some people maybe know, some maybe not know. In our software, so we have this, or here is called XPS knowledge view. If you click here, get this knowledge view, and then you can click this periodic table. You can find this for the useful information for any element. It's like this here, tell you titanium and what is this shift for the different bonding and give you a spectrum. So this software is a free downloadable. So if you have, enjoy to use that. If you don't have, and you can email me, I can send you a link, and you can download and get the license. That is quite useful, very user friendly, and maybe people never use this. And for the basic training and today, and I just like a basic operation, you have software. If you go to the help file, you can find. Okay, you can find it here. So this quantification, this operating at the help file, really, they have detail. There is, you can learn more than from me, and that is very detailed, tell you how to use, how to do the analysis stuff. You can look at the help file. Okay, so this half hour, and I'm going to talk about this, what the basic XPS and what they can do, and what advantage, disadvantage. And the next time I can answer a few questions.
Nice job, Sinchi. I'm enjoying it. There are a lot of chat comments. Maybe you can start with that.
Yeah, I can go to the chat. And this one, yeah, I look at the question. And with all these electrons come off, do you need some of sort of the charge? Yes, so that is, I mentioned that charge compensation. And that is a good question. In the picture I showed, for the insulating sample, the electron come out. So that is the surface will be, if it's the insulating, surface will be charged. And we have actually, for this instrument, that is not just the low energy electron, that is low energy electron plus the argon ion. This combination they find is much more effective for compensate. That is, yeah, so we can analyze all the solid sample. So we have charge compensation. So second is to avoid minimize charge buildup. And then this one, and that is like a SEM, you need a minimize is to do the coating. But for this XPS is surface analysis, you cannot do any coating. You don't need to this preparation. It's the charge buildup doesn't matter. We have a very effective the charge compensation and method. You just turn on the flood gun, and then you will no problem for any sample. So what the maximum film thickness for do depth profile? And is there the thickness criteria for this? Actually, theoretically, and you can do even micron, just take time. Just take time. Of course, you cannot do too deep. You said I want to do 10 micron or some 100 micron. That is, first of all, not realistic. Take a very long time, maybe take a week. Second is, You know, the X-ray, they shoot from side, they have an angle. Okay, they have a spot like 500 micron. For example, you use 500 micron or 200 micron. If you go to deeper, like 10 micron, of course, from the edge, and the shadow, something, you cannot do the analysis there. And for realistic, and typically use analysis from a field 10 till a field 100 nanometer. That is commonly used. More than micron is possible, just take super long time. And how do you know based on the element peaks need to fit with multi-peak? Okay, this fit the peak. Basically, you based on the peak shape because our use a monochromated X-ray and our X-ray the resolution is pretty high. If you get your peak is very broad or you have shoulder, you can compare with our like handbook and or compare with our knowledge. You can open that file for that element, you will see that. And based on that, if you find your peak have a shoulder, have a split, that you should think about do the peak fitting. And yeah, so that is for the peak fitting, really that is not and you need to do some homework. And based on your sample, based on this element, you should know what kind of chemical status, how many bonding they have, and for your sample, how many possible they have, and then based on the shape, you do the fitting. You have to understand or can explain for each fitting over there. And how do you, okay, how to deal with the background as the high energy side of the spectrum? This really depends on the sample, and this, as I mentioned, all the background come from the electron, and with inelastic collision. For some sample, the electron come out that is from the top lip. Yeah, there's no, that is really depends on sample. For the instrument side, we cannot do anything. So I know that seems like for the polymer sample, that is background is much high. And this, what determines the strength of the peak? And for example, in the silicon spectra, you mentioned the silicon 1+ and the strong and the 10+ and the weak. And okay, so this stronger, you know, if you look at the this 1+ and the strong or weak, okay, that is because the, for my Z spectrum for silicon, because silicon 4+, that is strong, because that is most bonding. That is based on how many they have, and how many bonding of the 4+, how many is element, how many 1+ is very less. That. And if you look at the whole spectrum, for example, for one element for silicon, 2s, 2p, some peak is strong, some peak is weak. That is based on the characteristic of this element, this core shell. And that is some peak that is they call the sensitivity factor. That is some is strong. Or we can say this electron easily can knock out. Some is weak and hard to knock out. That is all based on the research. We already know that. So that's why we have a sensitivity factor. So all your do the quantification in the software already considered the relative sensitivity factor, and they have to consider that, because you cannot simply use that is okay, this stronger, that is more, that is less, that is peak weak, that is less. No, you have to be considered that is a sensitivity factor. So if it's manually calculated, you have to be divided by that. But if you use the software, that already considered. How reliable depth profiling for very thin texture sample and like and powder sample? Yes, that is a good question for the powder sample for depth profile. So we all talk about the depth profile is for ideally that the film that uniformly going down. When you do the depth profile for the powder, for example, you have a particle. You have a particle. So that is X-ray and the argon ion. They're the two different angles. from two different sides of your particle, so sputtering. So that will be certainly the shape will be affect that. And also that is like a shadow side. And when you do sputtering, for example, and on the face to the argon, that is etched quicker. Another side, of course, maybe no etching or etch weak. For the X-ray, they still analysis that. Yeah. So we all talk about is ideal for the film. For the particle, that is complicated. Also, I also mentioned that for the training, sometimes I mentioned about when you do the depth profile, if your particle is very small, maybe your first particle already knocked out, your second particle surface just exposed. So that will be complicated. Does argon profiling is useful for sensitive material like a battery in order to extract the oxide state provided? Surface from surface to substrate. Argon profiling useful. Yes, that is. I don't know for this material and argon profiling. So argon, you have to be know if that is affect your material or not. If this argon sputtering can degrade your material or change the status. For example, I know that some argon can change the oxide for some material that they need to be careful and maybe do some more research on this. And could you talk a little bit about spectral fitting and, for example, how to set up this? Okay, for spectral fitting, of course, for this talk and for many people, I cannot talk too much. For this fitting, and we can see side by side and can show you. And for the training, basic training, just very quick for that. If you have some spectra, you have to do the fitting, and we can do like now, especially I can remote access that. We can use Zoom meeting. We can set up some spectra. We can, and I can show you for that. And I think that is we set up a separate meeting will be easier to do this fitting. Okay. More questions or maybe no. Yeah, if you didn't type and if you have question, you can talk now. Okay, so what orbital is the best to determine the oxidation state? Okay, so what orbital? Here is people often comment about, okay, I have 2s, 2p, or 3d. Which one I should use it? What one you should use? You should use commonly used by others. For example, like for silicon, you have 2s, 2p. Why we use 2p? Because everybody, and if you look at the literature and look at paper, all you have the 2p. And then they tell you for the 2p and how much is the shift from 99 till this one. If you use another peak, you cannot find the literature. You cannot find the database. People, did analysis. Also, theoretically, they should be similar. The shift, all shift maybe 2 eV, or maybe for that a little bit different, 1.5. You don't know. So you have to use this orbital is people commonly used. Our database have that. Okay, don't use. Sometimes if your peak is overlap with other elements you want to identify, you can use different peak. For example, if you have this element, you should have all the peaks. You can use other peaks to identify the other peak, not overlap. But for this quantification, for the chemical analysis, you need to use a common peak. Every people use. Okay, what about the compare across P block? Compare P block. Business system. Compare what? Compare this element.
So say I'm interested in, also, hi, thank you so much for the talk. But say I'm interested in comparing like a transition metal bismuth intermetallic to a transition metal antimony intermetallic, and I'm interested in the like the relative oxidation of those. How do you decide which peak is the right one to use in that case?
Yeah, for all this one, for this and tin or bismuth. So I think that is just as I mentioned, you from the handbook, from that knowledge book, all they tell you which peak you should analysis. Actually, if you for this peak, if you from our software periodic table, You click this, they give you a default one that is camera used.
Can I add one quick thing, Sinchi?
Sure.
Alexandra, in which form are these? Are they powder, crystals, compounds?
They're like pucks. They're like little pellets.
Yeah, so you can, obviously, if you're looking for surface, XPS makes sense. But the other technique like EELS, energy loss spectrometry, can also go inside, so you get more internal. And there are ideas of shift of the peak, but also ratio of the various peak they reflect. So, a little bit information, and I'm sure Xiaobing and others who are not in part of Cake 2 can also at least shed some light on your questions.
Thank you so much.
Who do you work with? Whose group is this?
I'm in Dana Friedman's lab in the chemistry department.
Okay.
Yeah.
Oh, well, but science prevails regardless of where she ends up, right? So, all right. Good job, Sinchi. Keep it up.
No question.
So what's the delivery time for your M6, huh? When you're likely to get it installed?
Yeah, that one I think is if we get new XPS, I think that it will be quicker. And if we order, and I think maybe after fall. Yeah, that we are very excited about that one. And I think if we, of course now we just probably talk about it. If we purchase that one, our user will be very excited also because the software is the same. They just get maybe just 20, 30 minutes training, and then they can use a new one. And they use new instrument. They never worry about the drop sample inside. I know the old one, some drop samples, every time they transfer, they get scary. For the new one, they never worry about that automatically. And yeah, that is very excited about that.